Hi, my name is Jim, and today's topic is the frequency response of operational amplifiers. And before we start discussing the details, let us couch this in a real circuit world. Suppose I have a microphone, and the typical output level of a microphone is from -40 to -60 dBV, and that relates to a given sound pressure level. And suppose we want to get this up to 1 volt output, and that would be also our reference level is 0 dBV, 1 volt, and I desire a frequency response here of 15 kilohertz. Now there's a lot of other factors that we might want to take into consideration that we'll talk about a little bit later. So we'll assume that our microphone is center range on this and has an output of -50 dBV. So what we want to do is basically have 50 dB of gain. So to figure out if the op-amp can do that, I have to convert that from the log domain into the linear domain, and I've done that here is standard form. Decibels equals 20 log of our gain, which is a ratio of output over input. So that may sound a little bit more familiar when I explain it that way. And then we just take the analog and solve that and see that we need a linear gain of 316 to take our microphone output up to a level of 1 volt. Now, the question is can a 741 do it? Let's find out. So first we're going to look at one of the parameters of an op-amp, and that's called the unity gain bandwidth. And unity gain is referred to as 1 here or 0 dB. And exactly what's the bandwidth going to be? So for an non-inverting configuration operating at a gain of 1, we're going to let that be 1 megahertz. And that falls within the range of the specified unity gain bandwidth for an LM741, which is a relatively poor 737 kilohertz up to 1.5 megahertz. Now, when you think about this, and if you get into designs, you have to look at a lot of different things. Data sheets have minimums, typicals, and maximums. Sometimes you use a minimum, sometimes you use a maximum, and what you always want to do is conservatively design so your device is going to work under a part made on a Monday or a part made on a Friday, part made by this manufacturer, part made by that manufacturer. So we're just going to use 1 megahertz at the present time, and then we'll digress a little bit later and see what happens. It's a nice number, not too high, not too low. So what we require here is a gain of 316, and I've expressed that as a unit of volt per volt. It's unitless, but you see this in data sheets sometimes, so I just want to use it, so be kind of familiar with it. And we're going to let our UGB be 1 megahertz, and I want this to be sort of high fidelity, so I'm going to let the upper cutoff frequency be 15 kilohertz. So can a single gain stage of 741 work? So what we have to say is we have the gain bandwidth product here, which is basically what it says. The gain of the operational amplifier times the bandwidth. The product of the two has to be less than the unity gain bandwidth of the operational amplifier. So that's what the GBP is. Not really simple to work out. It's the gain times the frequency of interest. Is it less than UGB? Let's find out. So I have 316 of gain times 15 kilohertz, and that comes out to be 4.74 megahertz. So that only exceeds the UGB of the 741. It drastically exceeds it. So let us go on with this. It will not work. We're not going to be able to get 15 kilohertz at that gain through the amplifier. It's going to act as a low-pass filter. So let's see exactly how low a frequency that this will actually work at if we in fact come up with the ratio of RF over RI plus 1, and that's the a non-inverting gain formula. So let's find out what frequencies that it'll work up to. So again, what I'm going to do now is simply solve for F in this. And when I do that, it's 1 megahertz divided by our gain of 316, and it comes out to be a relatively poor 3.14 kilohertz. And that's actually less than the telephone company's specification for voice band communication over the plain old telephone system networks, standard phone. So that's really, really missing the mark a lot. So suppose we look at this from the other standpoint. What if I had a gain of 15 kilohertz? What amplification would support that gain? So what we're going to do now is solve for the other variable. And again, it's the amplification times the frequency bandwidth of interest in our circuit equals UGB in this case. And then I'm going to solve for A, and I find out that the amplification, instead of being the 316, will only be 66.7, and that will support a 15 kilohertz bandpass. Quite a swing and a miss on that. So it looks like a single stage of using 741s is not going to work. Well, what if we put 2 stages in series? So this is called cascading, and I've kind of designated RF sub 1 and RI sub 1 and 2 here. This is called stage 1 to stage 2. So what we'll do to start with here is to set the gains of these to be equal. Now there are far better ways of adjusting the gains of these circuits with a single pot, and making them equal is going to serve a simple purpose for explanation, but maybe not be the ideal thing to do. After all, if I'm truly interested in something that's high quality, I have other concerns, like noise. What's the noise of a 741? Would it be better to have this gain be higher than this gain? Which is probably going to be the case, but I don't know. Matter of fact, is this the right part? So anyway, if we use equal gain here, what we have is the gain of the first stage equals the gain of the second stage. And to put that in English, the ratio of R sub F1 and R sub I1 is equal to the ratio of these two. And that'll provide for equal gain. So to figure that out, we have A1 equals A2, and then the product of 2 of them is the desired gain that we want, which is the 316 volts per volt. So to find A, I just represented this by A squared here. All we have to do is take the square root of 316, and that means that each stage will have a required gain of 17.8 volts per volt. So if we multiply 17.8 times 17.8, we come out with approximately 316, which will give us our 0 dBV, 1 volt output. Now, the other question is will this 2-stage approach work? Got the gain figured out, but I don't know that it's going to work, so let's go back and take a look. A times F question mark less than our 1 megahertz unity gain bandwidth, and multiplying this out comes out to be 266 kilohertz, which is definitely less than 1 megahertz. So this appears that we won't be crashing into the wall, so to speak, with regard to our unity gain bandwidth. Now, remember that when we open this little dialogue, what we said is the unity gain bandwidth minimum was 437 kilohertz. That's your design spec. You used a minimum gain, and this here is less than the minimum, so this looks like a safe design. With a range of 437 to 1.5 megahertz, there's all kinds of things you need to take into account, and once again, you need to be conservative. So if we summarize this in the graphical form, is everything we've talked about here is a compensated op-amp. And what that means is that the manufacturers place a fairly large capacitor, a nominal 30 picofarad in the case of a 741, at a critical node inside the op-amp, and what that does is it dominates the frequency response. In other words, we have, say, electrical circuit numerous R's and numerous C's, and each one can produce its own critical frequency. Here perhaps one out here and so forth, so there'll be multiple corners in the frequency response. So dominant means that this is overwhelming, and what it basically does is it severely limits the performance of the amplifier, but makes it just about unconditionally stable at any gain. So the price of performance is compromised for stability. Now if we just take a look at this, and this is not the scale, I have UGB here, and the gain's kind of logarithmically spread out here. And what we're going to notice is that with a gain of 1 unity, we can go all the way out and hit the unity gain bandwidth specification. So the unity gain product, gain bandwidth product would be equal to the unity gain bandwidth at that gain setting. And as we increase the gain, we're going to be running into our open loop gain curve, and that will curtail the frequency to these values. So every one of these would have a frequency that when multiplied by the gain would be equal to the unity gain bandwidth. So that's kind of the thought of it, is that as we change the gain and find out what the critical frequency is, that product for all of these should be a constant, which is the unity gain bandwidth. So the only other thing we have to be careful of here is that if we're using an inverting buffer where R would be equal to R, the gain of this is going to be -1, but the bandwidth of this at unity gain is 50% of the unity gain bandwidth. Now on a true logarithmic chart, what will happen is you'll see that 500K, say, quickly converge with this as the gains go up. But if you're using an inverting buffer, just keep in mind that 500K would be the unity gain bandwidth of that circuit operating at unity gain. So in conclusion, it'd probably be a better idea to look for a more contemporary operational amplifier. And with gains like that, in the 316 range, looking at an uncompensated op-amp, NE5534 comes to mind. It's very, very popular, low noise, high power op-amp used in audio circuitry. It was made in the late 70s and is used today in console design. So the folks at Signetics did it right, and they were bought out by Philips. But anyhow, what that would look like would be something like this, and a regular compensated op-amp might look something like this. So what we see here is that we have considerably more bandwidth at unity gain, but this here is going to be a pole, and it's not dominant. It's not like this. And dominant, I mean that there's only one critical frequency. So for the blue guy, we have one here, and do note that when, thinking back to AC, when the absolute value of X sub C equals R is defining that point, and that's also going to produce a phase shift of 45 degrees. So let me write that down. Now, due to other parasitics in the integrated circuit, because the manufacturers do not strap it with an internal capacitance, we have another pole, another critical frequency out here. And its phase shift is also going to be 45 degrees. Now, as we move from this point, we're going to be approaching 90, and then we're going to be picking up another 45, eventually coming in down here, maybe at something close to 180 degrees phase shift, as in real nice oscillator. So if we elect to use a uncompensated op-amp, basically the gain, and that would be the settings of RF over RI, would have to be at this level or greater. And we just might be able to pull off a single stage by doing that. So it's kind of strange when you think about stability that you're specifying a minimum gain, where you think that You know, the lower the gain, the more stable it's going to be. Not in an uncompensated op amp. And the word compensated and uncompensated are very, very important when you're looking at a design. So that should pretty much clean up this topic, and thank you for watching.